known in Europe as the Mayer-Norton theorem. Norton's theorem holds, to illustrate in DC circuit theory terms, that any linear electrical network with voltage and current sources and only resistances can be replaced at terminals AB by an equivalent current source, RNO, in parallel connection with an equivalent resistance RNO. This equivalent current RNO is the current obtained at terminals AB of the network with terminals AB short-circuited. This equivalent resistance RNO is the resistance obtained at terminals AB of the network with all its voltage sources short-circuited and all its current sources open-circuited. For AC systems, the theorem can be applied to reactive impedances as well as resistances. The Norton equivalent circuit is used to represent any network of linear sources and impedances at a given frequency. Norton's theorem and its dual, Thevenin's theorem, are widely used for circuit analysis simplification and to study circuits' initial condition and steady-state response. Norton's theorem was independently derived in 1926 by Siemens and Halske researcher Hans Ferdinand Mayer and Bell Labs engineer Edward Laurie Norton. To find the equivalent, find the Norton current RNO. Calculate the output current, IAB, with a short circuit as the load. This is RNO. Find the Norton resistance RNO. When there are no dependent sources, there are two methods of determining the Norton impedance RNO. Calculate the output voltage, VAB, when in open circuit condition. RNO equals this VAB divided by RNO. Or replace independent voltage sources with short circuits and independent current sources with open circuits. The total resistance across the output port is the Norton impedance RNO. This is equivalent to calculating the Thevenin resistance. However, when there are dependent sources, the more general method must be used. This method is not shown below in the diagrams. Connect a constant current source at the output terminals of the circuit with the value of 1 ampere and calculate the voltage at its terminals. This voltage divided by the 1A current is the Norton impedance RNO. This method must be used if the circuit contains dependent sources, but it can be used in all cases even when there are no dependent sources. Example of a Norton equivalent circuit. In the example, the total current E total is given by the current through the load as N, using the current divider rule, and the equivalent resistance looking back into the circuit is. So the equivalent circuit is a 3.75 mA current source in parallel with the 2 kΩ resistor. Conversion to a Thevenin equivalent. A Norton equivalent circuit is related to the Thevenin equivalent by the following equations. Queuing theory. The passive circuit equivalent of Norton's theorem in queuing theory is called the Chandy-Herzog-Wu theorem. In a reversible queuing system, it is often possible to replace an uninteresting subset of queues by a single queue with an appropriately chosen service rate. Bibliography. Britain, J.E. Thevenin's theorem. IEEE Spectrum 27, 42. DOI 10.1109, 6.48845. Retrieved 1 February 2013. Chandy, M. Herzog, U. Wu. Parametric Analysis of Queuing Networks. IBM Journal of Research and Development 19. 36-42, DOI 10.1147, Road 191.0036. Dorf, Richard C., Svoboda, James A. Chapter 5 Circuit Theorems. Introduction to Electric Circuits. Hoboken, N.J. John Wiley & Sons. pp. 162-207. ISBN 978-0-470-52157-1. Gunther, N.J. Analyzing Computer Systems Performance. With Perl, PDQ. Berlin. Springer. p. 281. ISBN 3-540-20865-8. Johnson, D.H. Origins of the Equivalent Circuit Concept. The Voltage Source Equivalent. Proceedings of the IEEE 91. 636 to 640. DOI 10.1109, JPROC 2003.811716. Johnson, D.H. Origins of the Equivalent Circuit Concept. The Current Source Equivalent. Proceedings of the IEEE 91. 817 to 821. DOI 10.1109, JPROC 2003.811795. Mayer, F. Über das Ersatzschema der Verstärkerrohre. Technical Report Trademark 260-1860 Design of Finite Networks for Uniform Frequency Characteristic. Bell Laboratories.